Test. Okay.
Sure.
I'm tempted to not move on until we determine what these half reactions are. Redox reactions. Redox reactions. Redox reactions. Also the same as oxidation reduction reactions. What are your two half reactions?
Oxidation reduction.
Thank you.
Okay.
All right.
I thought that was too obvious.
Okay, I told you not to think too hard. So step 2 is to determine your half reactions. Determine your half reactions. After you do that, we're going to balance by mass. Balance by mass. Then we balance by charge. Then we're going to cross multiply, add, and simplify. And finally, we will check our work. So here are your 6 steps of balancing a redox reaction. Convinced? Sweet. So let's do an example so you can see how it actually works. If we have iron 2 and MnO4, and we are producing iron 3, manganese 2. Let's produce the balanced redox reaction for this reaction. Okay. Step 1 is to assign our oxidation numbers. So what is our oxidation number on iron 2? 2. Right, remember, on a monoatomic ion, your oxidation number is equal to your charge. So our oxidation number on iron 2 plus will be +2. How about our manganese and oxygen here? What's our oxidation number on oxygen?
For one of them, or?
Yep.
Is it -2?
-2. Very good. So unless dictated by hydrogen or fluorine, oxygen will have a -2 oxidation number. If it's in a peroxide, it'll have a -1. But almost always, when you see oxygen, you should know it's -2. How many oxygens do we have? 4. So what is our total oxidation number from our oxygen? -8. So what does that mean? Our oxidation number needs to be on our manganese. +7. Does that make sense to everyone? +7. We only have one of them, so our oxidation number on that is +7. Over over here, what about iron 3? +3. And manganese 2? +2. So we've assigned our oxidation numbers. Does anyone have any questions on that? No. Okay. Next, we determine our half reactions. So what is our oxidation half reaction? Well, our iron went from +2 to +3, and our manganese went from +7 to +2. So which of those was oxidized?
The iron.
The iron, right? Because it got more positive. We went from +2 to +3. So for oxidation half reaction, we're going to write Fe2 plus becomes Fe3 plus. So we're going to write out our oxidation half reaction. So the half of the reaction that pertains to our oxidation. Next, let's write out our reduction half reaction. So we go from MnO4 minus to Mn2 plus. So we've put all of our reactants and products in one of our half reactions, so we're good to go there. And we've identified which is oxidation and which is reduction. Makes sense? Following so far? Okay. So step 1, we assigned our oxidation numbers. Step 2, we determined our half reactions. Step 3 is to balance by mass. So when we balance by mass, we can do that 2 ways. We're in acidic solution, so we can either add H2O or we can add hydrogen. So we can also mess around with our coefficients if we need to, but for the most part, we're adding water or hydrogen. So you'll see we don't add oxygen directly. We can't just say +4 will balance it. Any oxygen that we add comes from water. So we look at our first reaction, our oxidation reaction. That is balanced by mass. Right? We have 1 iron here, and we have 1 iron here. So we're good to go there. Next, we move on to our reduction reaction. We have 1 manganese here, 1 manganese here. We have 4 oxygen here, and no oxygen here. So what do we need to do to balance our reduction reaction by mass?
Add water
To which side?
to the right side.
How many?
4.
Right. So +4 H2O. Okay. Now, do we need to do anything else?
Yes.
What else do we need to do to make sure we're balanced by mass?
You need hydrogen on the other side.
Right. So just like when you're balancing a combustion reaction or a precipitation reaction, any reaction that you're balancing, as you add things, as you mess around with coefficients, you're going to change the amounts on each side. So we have to go back and make sure that we are good to go. So we're going to add 8 protons, 8H plus. Remember that it's H plus and not just hydrogen. We're going to add 8 protons. Okay. Now we're going to go through and balance by charge. So we've assigned our oxidation numbers. We determined our half reaction. We balanced by mass. Now we need to go ahead and balance by charge. We balance charge by adding electrons. Adding electrons. Remember that electrons carry a negative charge. So when we add them, we're reducing the overall charge by 1. So let's look at our oxidation half reaction. We go from Fe2 plus to Fe3 plus. we're not balanced by charge right now, because if we add up all the charges over here, we get 2. We add up all the charges over here, we get 3. So what do you think we need to do to make sure we're balanced by charge? Say
You need to add another electron to the left side somewhere. Is that what we're doing?
the left side.
Oh, my bad,
You pointed to the right side.
Yeah.
Okay. So we're gonna add 1 electron. Just like that. Add an electron. Because what really happened is this Fe2 plus had an extra electron with it. And now when it became Fe3 plus, it gave up that electron. Right? So really we're illustrating what's actually happening when we go through and balance these. Remember that redox reactions are the transfer of electrons from one species to another. One is oxidized, one is produced, one gains electrons, one loses electrons. So your oxidation reaction should always produce electrons, and your reduction reaction should always consume electrons. Does that make sense? When you do this, you should always end up with electrons on opposite sides of the reaction. So now we need to go through and balance our reduction reaction by charge. We have, what if we add up all the charges on our reactant side, what do we get for our reduction reaction? Kind of autofocus. Oh well. We add up all the charges on this side, what do we get?
Zero.
No. A pluses,
Oh my gosh.
1 minus, 8
Look at that.
minus 1, 7. Wow, you guys are talkative. I stand by my statement when I walked in the room. All right, 8 minus 1 is 7. So we have plus 7 over here. Plus 7 over here. What do we have over here? Plus 2. Plus 2. We have plus 7, and we have plus 2. So what do we need to do? How do we make sure that we are balanced by charge?
Do we add electrons?
That's the only thing we can do. Balance by charge.
Okay.
Add 5 electrons on the right side,
Left side.
left side.
Does that make sense? So remember, electrons carry a negative charge. So we have 8 minus 1 minus 5 gives us plus 2. And here we have plus 2. Does that make sense?
Okay.
Minus 5 plus 8 minus 1 gives us plus 2. Here we have plus 2. Does that make sense? There's no way to add a positive charge. If you do this enough times and you don't like it, you could just as easily subtract electrons from this side. Okay, we won't do an example of that because I don't want to confuse you. But just like the other side, if you were to subtract a negative charge, right, 2 minus negative 5 would give you plus 7. So now we're balanced. So we assigned our oxidation numbers, we determined our half reactions, we're balanced by mass, and now we're balanced by charge. Next step is to combine them. Cross multiply, add, and simplify. So we're going to reintegrate our 2 half reactions. Does that make sense? and put it together. Okay. It's like if you're cooking, you mix the dry ingredients, you mix the wet ingredients, and then you put them together to bake a cake. That's what we're doing here. Okay. Ryan's looking at me like, I don't know, just put it on a bowl. Okay. So we want our electrons to cancel. We don't want any free-floating electrons in there because any electrons given up by one thing should be accepted by a different thing. Right? That's the whole idea behind redox reactions. So for every 1 unit of this oxidation reaction, we produce 1 electron. For every 1 unit of this reduction half reaction, we consume 5 electrons. So we're going to multiply our oxidation reaction times 5 and our reduction reaction times 1. That's why I wrote cross multiply. 5 and 1, because when we're done, we should have our electrons cancel. Does that make sense? If this was 2 and this was 5, we multiply by 5 and multiply it by 2 so that we yield 10 both ways. Right? 5 times 2 and 2 times 5. Does that make sense? Kind of, sort of. So we're going to get 5 Fe2 plus becomes 5 Fe3 plus 5 electrons. And we're going to have 5 electrons plus 8 protons plus 1 MnO4 minus becomes Mn2 plus 4 H2O. After we're done multiplying through. Does that make sense? Yes? No? Now we're going to recombine them. So we're going to add our reactants together and our products together. And we'll be left with 5 Fe plus 5 electrons plus 8 protons plus MnO4 minus plus 5 Fe2 plus becomes Mn2 plus 4 H2O plus 5 Fe3 plus 5 P minus. So we're going to combine them together. Does that make sense? What doesn't make sense about this so far? We'll start there. Any of the steps?
Wait, is this the final answer?
No.
Okay.
Well, yeah, let's get to the final answer and then we'll talk about
Okay.
it. Cross multiply, did it, add it, did it, simplify. So if we have things on the reactant side and on the product side, we would cancel them out. In some cases, I'll do an example, you'll have water on both sides. So if you have 2 water over here and 4 water over here, you can cancel it out and just be left with 2 water over here. 4 minus 2. In this case, the only thing that's going to cancel is our electrons. So you can go through and cancel that. Just shoop. Shoop. All right. Electrons are gone. This is our final answer. We can go through and check our work in a couple of different ways. The sum of our oxidation numbers on both sides should equal. The sum of our oxidation numbers on both sides should equal each other. Let's take a look at that. So here we have +1 and we have 8 of them, so we have +8. Here we could go through and do this automatically, right? -2, -8, +7. We know they have to add up to be -1. Moving on, we have 5 times a plus 2 would give us plus 10. When we add all of these together, we get 8 minus 1 plus 10, we get plus 17. Do the same thing over here. Well, plus 2. We could do this, minus 2 plus 1 plus 1, but we know they have to add up to be 0. We're not getting anything there. 5 times 3 gives us 15. 2 plus 15 gives us plus 17. So our oxidation numbers are equal on both sides. That means we didn't mess up along the way. And we have our final answer. You will notice because your oxidation numbers are directly related to the charge on the compounds, if you add up the charges on both sides of the equation, they will also equal each other.
Did that H2O cancel out? Is that why there's nothing underneath that?
Yes. Right, so you have minus 2 plus 1 plus 1, you'll be left with 0. And we know that because the charge on water is 0. Otherwise, we would likely all die. So, what questions do we have on any of these steps? Don't say you don't have any questions, because if none of you have any questions, we're going to do another example.
No, I have a question. All right, stop. Where did that plus 7 come from? Way up top.
Way up top. Plus
Way up
7.
top. Where did it come from?
So you have MnO4 minus.
Yes.
You know that oxygen is minus 2 in compounds.
Yes.
So you have minus 2 from each of the oxygens, which gives you minus 8.
Yeah.
So the sum of the manganese and the oxygen need to give you the charge on the compound.
Okay.
So what minus 8 gives you minus 1? Or what plus a negative 8 gives you minus 1? And that's a positive 7. Does that make sense?
Yes. I was just going the other way. Now it's all coming together.
Why didn't you stop me like a half an hour ago?
Because I was confident I was going to figure it out, and then it went down the street.
How are we doing otherwise? What other questions do we have?
Still a lot to keep track of.
It is a lot to keep track of. If you follow your steps, it will always work. Now, something about the steps. If you're going to do it this way, it is very, 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 very important that you first balance by mass and then balance by charge. Because when you balance by mass, you'll often be adding protons. Protons carry a charge. That's going to impact when you balance by charge. Now, the number of electrons that you're adding is directly related to the change in oxidation numbers. So for your oxidation reaction up there, we went from Fe2 plus to Fe3 plus. So when we break down our half reaction, we're going to add 1 electron, because if we look at our oxidation numbers, we have plus 2 and a plus 3. So if we were just to hypothetically balance our oxidation numbers, we would need to add 1 negative charge. Does that make sense? Now, if you look at your reduction reaction, that's going to be the same way. Our manganese went from plus 7 to plus 2. So right off there, you could know that you're going to have to add 5 electrons when you balance by charge, because you have to justify your oxidation, the change in your oxidation number. This is a more systematic approach to it, but both will work. If you really wanted to, you could balance by charge first. If you, well, not even really balance by charge, but balance by oxidation numbers. But I would always recommend following these steps in order. Okay? So your oxidation numbers, determine your half fractions. Those first 2 steps you've already done. Right? You're used to doing that. You're used to seeing a reaction, determining your oxidation numbers, drawing your arrows, doing whatever you do to say what's oxidized and what's reduced. there's really no difference between identifying your half reactions and determining what was oxidized and what was reduced. That's the same thing. It's just writing it down instead of drawing it down. The next two steps are basically the same, right? You want to balance your reaction, mass then charge. And really that's it, right? Then you just put them back together. Take them apart, put them back together. Check your work. If you did it all correctly, you don't have to check your work. I would recommend checking your work, at least until you can do these in your sleep. Are you ready for an example? For you to work on your phone. If you're not, you should ask a question. And then we can clarify whatever's confusing. Otherwise, we're gonna wing it. See what you can do. Another example. All right, you ready?
No. You really giving us an example?
Yeah. It won't be a really bad one.
Right.
I don't think. Oh, that's one that's fun. Oh, okay, I don't want to do that one yet. Oh, this is fine. Ooh,
No. No.
what?
You know, it's gonna be interesting when he looks at
No,
the
I bet it's
periodic
gonna have
table.
polyatomic ion on it.
Ah,
That's why it did that.
now we're thinking. So. VO2 plus methane to produce vanadium dioxide plus bicarbonate. Go for it. I don't even know what that is. Vanadinite? Vanadium?
And you said VO2 plus, and I'm like, oh, is V even a thing?
Yeah, it's vanadium.
Is that a Y or a V?
It's a V.
What's a V? What are you looking for?
I don't know what the chart is on. Amazing.
Google's not gonna help you.
What do you mean Google's not gonna win? Google has everything.
Google will give you a list of possible charges of vanadium.
Well, that's fine. I just need to know combines with dioxide.
Oh, I know where you're stuck. All right. 30 more seconds and we'll reconvene to at least determine what it is that I wrote on the board. And then I'll let you go ahead and continue the redox reaction. Or we can restart and talk about chapter 1 again.
Oh, gosh, don't go that far back.
I've gone over methane so many times, I should know.
Yeah. Stephanie, you got it? No? You stuck, same spot there stuck?
Yeah, probably.
Damn it! That's unfortunate. Oh well. All right. Methane. What is it? 1.
One, I know that.
So if you have 1 carbon and it's a hydrocarbon, how many hydrogens do you have? No. How many bonds does carbon make?
Not far.
4. 4. Four. 4 plus 4 is 8. 4 minus 4 is 0. 4. Don't do that. Okay. 4. So it makes 4 bonds. It's a hydrocarbon. We have 1 carbon. CH4. CH4. Vanadium dioxide. Katie, what's tricky about this?
I don't know what the charge is.
You don't need to know the charge. You know why?
Oh my
Because
god.
it's a covalent compound.
Oh,
We know it's a covalent compound because we have di. We don't use our prefixes for ionic compounds because we don't need them. Vanadium, V, dioxide, O2. VO2. 1 vanadium, 2 oxygens. Okay? All right? Bicarbonate. We've talked bicarbonate on Thursday and last Tuesday. Carbonate is CO3 2 minus. Bicarbonate is what? And not 2 of them.
HCl.
HCO3 minus. HCO3 minus. Now, go do your redox. What?
no. 2.
Everyone's in the class is now coming to this. What happened to the group that we had before finals? There are like 8 or 10 people here. Or before the exam. Before finals, the room's gonna be full.
Every time.
I'm gonna tell everybody, well, you should have come the last 16 weeks. Well, at the time when everyone realizes that they're not gonna be able to use their notes on their final, and that it's not gonna be online, they can't Google the answers, they'll get bonus points for drawing dinosaurs.
My drawing was good.
I'm sure it was.
So the CH4 and the VO2 don't have charges?
Right.
Okay.
Methane is not charged. No charges on hydrocarbons. For you biology people, bicarbonate is very important. Bicarbonate. I don't know what it's biology. Bicarbonate is very important. Because bicarbonate is one of the ways that we rid the body of CO2. Carbon dioxide reacts with water to produce bicarbonate and a proton. Bicarbonate is soluble in blood. Transfer it back to the lungs, convert it back to carbon dioxide, expel it. It also acts as a buffer system so that our blood doesn't become too acidic or too basic and eat us. All right, we ready? Who's doing the first step? Step one. Stephanie?
For oxidation numbers?
Come up and do it on the board.
Oh, up there. Oh,
On the
God,
board.
what? I
Yeah.
don't
Community effort.
know.
Okay. What are we doing?
Alright.
Yeah, let's just do this. Nobody's gonna watch this anyway, but I don't have anything to worry about.
Oh, thanks. Okay.
All right, so we've got oxygen, -2, two of them, -4. We need to add up to +1, so we're gonna have +5. Very good. Methane, +1, +4, -4, perfect. The general rule, carbon will traditionally be +4 or -4. As you can see there. Vanadium dioxide, -2 times 2, -4, +4 to get to 0, perfect. CO3 -2 times 3 gives us -6. We know hydrogen's +1. So we have to add up to get -1. 1 + 4 - 6 is -1. Very good. Haley, why don't you go up and,
Hey, I didn't even get that far.
well, now you see it. Ryan, do you want to go up and do our math reactions? Sure you do.
For multiple?
Nope.
Oh, then I'm not entirely sure.
We got an oxidation reaction and a reduction reaction. Take your best guess. The camera's off. Nobody's watching you except the three of us. And it won't change what I think of you. The only thing that'll change what I think of any of you is whether or not you can memorize polyatomic ions.
Oh my god. It's gonna go on your headstone, I swear.
What?
What?
Huh?
Okay.
Ryan, it's okay to be wrong. Go up and write something on the board. Ryan or Jalen?
I don't,
Somebody.
wait,
Draw your arrows and determine what was oxidized and what was reduced, and then you'll know what to do.
yeah, but on the other example, the charges were up top, like for Fe, 2+ up top, none of those have that. Oh,
Doesn't
except for
matter.
the one. It doesn't matter, I just go off the
Remember, we weren't
bottom.
looking at the charges, we were looking at the oxidation numbers.
Just the oxidation numbers?
Yep, that's all that matters. The charge doesn't matter. Now with monatomic ions, your charge is your oxidation number. But all we care about is our oxidation number. So what you're looking for your oxidation half reaction is which got more positive. And for your reduction reaction, you're trying to find out which got more negative. Somebody write it on the board. It's okay if it's wrong. It's a
But I-
perfect opportunity
But I
for us to
don't have an answer.
write something. And then we can talk about it.
Wait, I wrote.
On the board. Right? Go write it on the board, whatever you have, wing it.
I don't have anything.
Yes, you do. Stephanie, do you have?
I have arrows.
Okay, why don't you go write it on the board?
Okay. Where's the marker?
They both have a marker.
Okay.
Neither of them
Let's
knows
see.
how to use it.
No.
Perhaps you can show them.
And then I was kind of confused. I'm gonna join yours.
This one, because do you add like the two, like the chart, like what you have for the oxygen, since they're two separate pieces?
Does your oxidation number ever change on oxygen
Mm,
in this case?
No.
No,
Okay.
so that helps us.
So just take it to like one of them then, or I guess
So-
it wouldn't do anything anyways.
So you're gonna wanna draw arrows about things that changed.
Okay.
So oxygen didn't change, what else didn't change?
Carbon, wait.
Nope.
Carbon changed.
Hydrogen.
Hydrogen.
So don't worry about hydrogen, so we don't need an arrow there. Now we have two arrows.
Okay.
I would bet that one of those is your oxidation reaction and the other is a reduction half reaction. So which one was oxidized and which one was reduced? We're looking at vanadium and carbon.
Carbon lost electrons, so that'd be oxidized.
Carbon was oxidized, very good. So leave some space so we can add in whatever we need.
So how do you write it again?
So you've got your methane, right, CH4. And then just draw an arrow. And then we have our bicarbonate. Very good. All right. Ryan or Taylor, go write the reduction reaction. Very consistent. Ryan, stop worrying about whether it's right. Just go write it down.
I'm trying to write something down, so I go there and write something down.
Oh my God.
Taylor's gonna murder me by the end of the year.
Yeah, maybe.
Weapons inside. Oops, wrong. We're on the right track. So we want to keep them in the compounds that they're in. So
Right.
the oxidation reaction that's up there, the CH4 to HCO3 was correct. So use that to determine your reduction reaction. So rather than V5 plus, we would just write out VO2 plus. And that becomes VO2. Does that make sense?
Kind of.
All right. So unlike your ionic and your precipitation reactions, we can't separate out carbon. It's always going to be bound to something. So when we write our oxidation reaction, we're going to write it in the compounds that it's bound to. All right?
Okay.
We're going to do the same thing for our reduction reactions. We see that vanadium was reduced, right? +5 to +4. So it became less positive or more negative. And VO2 plus to VO2. So all we're doing, we're not changing anything about the compounds that are in a reaction. All we're doing is splitting them up into two half reactions. Does that make sense? So we're not changing anything about these. We're just putting them in different spots. Sweet? Does that make sense? So we don't have to break up anything. We just say vanadium was oxidized, so we took our vanadium containing reactant and our vanadium containing product, put them together. Vanadium was reduced. Carbon was oxidized. We take our carbon containing reactant and our carbon containing product, put them together. So we've assigned our oxidation numbers and we have determined our half reactions. Next, we balance by mass. So here we've got 1 carbon and 1 carbon, so that's good. 4 hydrogen and 3 oxygen. So similar to how we balanced with our combustion reactions, the thing that we're going to add last, we want it to be the thing that's by itself. So in this case, that's hydrogen, right? Because we can add hydrogen without affecting the quantities of any other element in the reaction. Does that make sense? So we've got CH4 and HCO3, so we need 3 more waters over here. I'm sorry, 3 more oxygens over here, and how do we add oxygen?
With water.
With water. So we're going to add 3 H2O to add our 3 waters. Next, so we're balanced, our carbons are balanced, our oxygens are balanced, we have to balance our hydrogen. We have 6 and 4, so we have 10 here and 1 there. So what do we need to do? Add hydrogen to which side and how many?
Add it to the right side and add 9.
9H plus. Right, and now we have 1 and 9, so 10. Over here we have 3 times 2 is 6 and 4, so we have 10 and 10. We are balanced by mass. Next. 1 vanadium, 2 oxygen, 2 oxygen. Our reduction half reaction is balanced by charge. So we are all set to go there. Good. Sweet. Now, we've assigned our oxidation numbers, we've determined our half reactions, we've balanced by mass. Next, we need to balance by charge. So, here we have a charge of 0 and a charge of 0, so 0 plus 0 is 0. Over here, we have -1 and +9. So what do we need to do to balance our oxidation reaction by charge? We've got 0 and 0 is 0, and here -1 and +9 is +8. So what do we need to do to balance our oxidation reaction by charge?
Add 8 electrons
To which side?
to the right side.
The right side. Because +8 minus 8 gives us 0. And that gives us right back to where we were from our reactant side. So we're balanced by mass, we're balanced by charge. Next, we need to balance our reduction reaction by charge. What do we need to do there?
Add 1 electron to the left side.
Very good. So remember, as long as we're adding electrons, they will go on opposite sides so that when we cross multiply, they will cancel out. We're balanced by mass, we're balanced by charge. Now what do we need to do?
Cross multiply.
Cross multiply. What are we going to multiply our first reaction by?
1.
1, because here we have 1 electron. What about our second reaction?
By 8.
By 8. Does that make sense to everyone?
Yes.
We want to end up with the same number of electrons on both sides. So we end up with 8 electrons plus 8 VO2 plus 3 H2O plus CH4 becomes 8 VO2 plus HCO3 minus plus 9 H plus 8 electrons. We know we're doing something right because we have 8 electrons on either side, which means they cancel, so we can cross them out, get rid of them, rewrite it without them, whatever we do. And now our last step is to check our work. Some of the oxidation numbers in our VO2 plus is going to be +1. +1 times 8 is +8. 0, 0, so plus 8. Over here, hydrogen's plus 1, we have 9 of them, plus 9. The sum of the bicarbonate will be minus 1, plus 9 minus 1 gives us plus 8. We have plus 8 on both sides, so we did it correctly. We checked our work successfully, and we have our final answer for our balanced oxidation reaction in acidic conditions, in acidic solution. Any questions on this? No? No questions? You all have a good handle on it?
Great.
Ryan, any questions? All right. It is 6:06. Sign in. Otherwise, then we are all set. You all have a wonderful night, unless you are staying for biology. Thank you. Have a good night. I'm straight.